Hello, everyone, and welcome to today's QA Wolf Conversation, 3 principles for building multi-agent AI systems. My name's Caleb Masters. I'm very excited to be your host and moderator for today, and I'm really excited to spend the next 30 or so minutes learning about this very important topic with you. But before I do, I'm very excited to welcome my co-presenter. He's the real star of the show. He's the director of AI at QA Wolf, Nishant Shukla. Nishant, welcome.
Hey, thank you so much for having me. Excited to talk about multi-agent AI, and let's just get started.
Yeah, let's jump right into it. Now, before we do, I want to give everyone just a little sneak peek at what all we'll be covering in today's conversation. So, first up, we're going to spend some time defining what exactly is AI. I mean, there's a lot, or AI agent specifically. There's a lot of different ways you could define agent, but what do we mean when we think about it from the QA Wolf perspective? Secondly, we'll talk about how multi agent AI systems compare to single agent AI systems. And then we'll move on to really the meat of today's presentation, which is the 3 core principles behind a successful multi-agent deployment in QA. And lastly, we'll close out by talking about how to use multi-agent models to improve efficiency and performance. Now, let's move right into topic number one, which is what do we mean when we say agent? Like, is it a secret agent, 007 sort of thing? Is it a person or a program or a bot? So, Nishant, give me the breakdown. What do we mean when we say agent here at QA Wolf?
Oh, it's all of the above. A agent is an entity that performs actions based on observations. We've heard the word agent a lot lately in marketing and AI literature. Everyone uses it, but I'd like to step back and just repeat what the reinforcement learning definition is. One other concept of an agent that's pretty relevant is the policy function. An agent is equipped with a policy function. The policy function is this function you see on the screen with the symbol pi. It takes in a state and produces an action. That capital S is the set of all states. The capital A is the set of all actions. This is the function that is basically powering the agent. It's the brain, decision-making brain of that system. Any person could be an agent. You're an agent. I'm an agent. Governments are agents. Families are agents. But we'll talk about agents that are implemented with large language models. Now, a policy function could be many things. It could be implemented by a random function, or it could be implemented various ways. So how do you define what is a good policy function as opposed to a bad policy function? One way you can say that is a optimal policy function is one that maximizes the expected utility. So I apologize, but now by introducing the word agent, I had to introduce policy, and then I had to introduce utility. And you're probably thinking, oh man, this is just going to go on and on. And it probably will. That's why so many textbooks have been written on this topic.
You're bringing in the fun words, Nishant. Policy, utility. But hey, I appreciate you bringing that up because there are a lot of technical terms that can be associated with agent, and I thought it might be best to start by learning a little bit more about maybe a more practical example that maybe people who are less well versed in that technical wording might be able to understand. So, could you provide an example for us?
Sure. Let's talk about a vacation planner. Imagine a chatbot that helps you plan your vacation. In 2024, this chatbot can actually do a lot more than just have a conversation with you. It could update your calendar. It could read your calendar. It could also search the web or book appointments. There's many things that this chatbot can do. It has agency, as we say it, and so that's why we start saying the word agent a lot, because now it's not just about being stuck in your computer showing you text and you give it text and you're just having a conversation, but it's actually affecting the real world. So when an action changes the real world, or when it affects the state, that ends up evoking this concept of agents. This chatbot example, it's also utilizing the policy function. Given a state, it will produce an action using its policy function. And so I covered a couple of these actions that it might do, but I would like to draw a distinction between actions that are read-only, like getting the weather, and actions that actually change the environment, like making a reservation for a restaurant that actually changes the outside world. And we call those actions, whereas we call these read-only things tools.
And now that you've kind of provided a good example for what is a single agent model, I want to move on to multi agent systems. So now that you've provided that context, can you elaborate on the differences between a single agent and a multi-agent model?
Yeah, multi-agent just has more agents. That's it. We're done here. It's that simple.
Webinar over. We're done.
Bye. There is a very good characteristic of a multi-agent system that is important to talk about. In a multi-agent system, we're really distributing the knowledge, the information, the input between the agents, such that no single agent might be capable of solving the problem on its own. So this implies we need to introduce some form of communication between agents so that they can actually solve the problem. So multi-agent systems are built up of individual agents that have some partial information, and because of that, they need to communicate with each other to solve that problem.
When you're thinking about the challenge that's associated with just doing a single agent, having a single agent driving your system, the way you laid it out earlier, thinking more agents, more efficient, maybe, but also a lot more variables, a lot more things that could go wrong, especially when you think about the potential challenge of getting a single agent to work effectively. So, why introduce more agents in QA Wolf?
Why make our life harder, you ask? Well, we tried one agent and we learned that there are some challenges with that. Specifically, when you have a single agent, you have to really represent the state space in a clever way so that you can represent all that knowledge, the HTML of the page, the URL of the page, all the history so far of actions performed. That state space becomes huge because one agent becomes a generalist that needs to solve all sorts of problems. So then it needs all sorts of inputs all the time. Also, it would have to produce an action for all possible actions it can do. Imagine a multiple choice test where you have 200 options. You can't randomly guess a good answer if you don't know how to solve that problem. But if you only had a 4-question multiple choice exam, you can get lucky and get the correct answer. So that just kind of shows how a smaller problem is easier to solve just because inherently it's easier, but also because each agent is an expert at solving that specific thing. So there's all these a couple factors that come into play to improve the accuracy in a multi-agent environment that you don't get as much in a single agent environment. And tied to accuracy is speed and cost. If the agent is not making mistakes, it's a lot faster to end that session and complete the problem. And also with cost comes just the load of the inference. If you're storing all that information and you have to use it, it can get expensive, especially with LLMs, as with the context sizes and just number of calls. It's slow and expensive. So with multi-agent, we kind of benefit from all of those accuracy, speed, cost issues.
Right. Yeah. Thanks for recapping that. So again, accuracy, cost, and speed. So in other words, if I'm hearing you right, when we think about this in the bigger context, the slower and more error prone the agent becomes, that's a challenge with a single agent. The more you give it, the less effective it is. What have you
Yep.
seen at QA Wolf? How does that contrast?
So far, so good. At QA Wolf, we've noticed a great impact in those metrics of speed and accuracy and so on. And I think it really shows that the proper architecture can go a long way.
What are some important considerations? I imagine a lot of viewers are watching today thinking, all right, well, you got me on board with multi-agent models in theory, but maybe there's some questions I should be asking or things I should be considering before implementing it within my company or within my team. What are your thoughts on that?
Yeah. So there are downsides to implementing such a thing. You have to be careful because it's a minefield out there. LLMs are new, and you could implement them incorrectly. So it's careful. It's important to be careful about how you implement them. And today, I really want to just have that discussion about our core principles of what is the right way to go about this. Because if you're not careful, you might trip and slow down your own progress.
Hmm. All right. Well, I appreciate you providing a little more information and background exactly how we think about multi-agent models. And again, I want to bring this back to the business context, which is here at QA Wolf, our business is achieving 80% plus coverage of end-to-end testing for our customers. End-to-end testing is a very complex process. There's a lot of variables, a lot of considerations, and there is a lot of human in the loop and interaction in terms of like trying to problem solve. So maybe you could elaborate here for me, Nishant. What has historically made end-to-end test maintenance difficult for AI?
Yeah, let me first just talk about what is AI good at. It's good at detecting images and what's in them and classifying them. It's also good at some regression problems like propensity or churn modeling. But why is it a little more difficult for AI to solve end-to-end testing? You can think of those other problems as single shot or one shot decision problems. Given an input, all you need to do is predict an output and you're done. But with sequential decision making problems, it's not just about that one decision or one prediction. It's a series of these predictions over time that constitutes like one session, and you're really evaluating the performance of the session. So inherently, it's a little more difficult just because a lot can go wrong within a session, especially in end-to-end testing. A lot can go wrong. For example, there are flaky tests. When a test fails, you might want to rerun it to double check whether or not that failure is reproducible. And if you cannot reproduce the failure and now it passes, that's a flaky test. You don't understand why it's passing now. There might be many different factors at play. It just makes it really hard to know what's going on. These little hidden variables, these hidden states that are happening in the real world are hard to model and capture. Another example is if you can reproduce the error, if a test fails and it fails again and it fails again, it might not necessarily be a bug. It just might be that the code itself is outdated because, let's say, the website has updated its UI, so now a button was renamed. That doesn't mean it's a bug. It just means we have to adapt the code to the changing environment. All of this makes it pretty challenging for the AI systems to solve that test maintenance problem.
Right. I see you have a number of frameworks on the screen here. Maybe you could elaborate on some of the frameworks that you looked at initially when trying to solve this problem.
Sure, luckily we're not alone, and there are other multi-agent frameworks out there. Unfortunately, though, we've grown a little bit out of them. There's a couple gaps we had to fill. There's just in that list on the right, you can see a couple concepts or a couple functionalities we've had to introduce into our framework that were either missing or just not up to par to our needs internally. For example, a hierarchical state representation system, which we call a modifier, is something we had to introduce, as well as a couple other things like the smart termination criteria, and the list goes on. But my point here is the challenges are the same, and the core principles to follow are also the same, whether you roll your own framework or use one of the open source solutions out there.
Yeah, well, again, I appreciate you showcasing a lot of the gaps and just highlighting here some of the challenges we ran into or some of the shortcomings we saw initially. How did the team go about identifying and solving for those gaps?
We just went full speed ahead until we hit a dead end, and then we decided to take action. And I really recommend that approach of when prototyping, just try either everything or just pick something and go full speed ahead on it until you really discover the problem, and then use that as evidence on making the next decision to decide whether to roll your own system or use an open source one. But really collect more data early and use that to drive your decision making for how to implement this.
Awesome. Well, thanks again for sharing the findings from the team. And I appreciate you providing that business context. It's going to be really important as we move into this next portion here because we're now going to be talking about the philosophical implementation here. So the QA wolf philosophy to achieve the most trustworthy results. So we know that you can't change the nature of end-to-end test, but based on what you've shared so far about the findings, it's clear that you can change the nature of AI systems. And that is why, to your point, Nishant, why we developed this multi-agent AI system to begin with. So Nishant, maybe you could walk us through some of these core principles that your team came up with when implementing, a multi-agent AI system to achieve faster, cheaper, and more accurate QA processes.
Sure, it's a double-edged sword with the multi-agent system. If you're not careful, you might trip and fall and end up not saving time. So if you follow these three principles, and these are the same three that we follow here at QA Wolf, you end up actually reaping the benefits of implementing this thing. So principle one, each agent should be an expert on a specific topic. Principle two, prioritize an evaluation benchmark to measure the end-to-end performance. And principle three is the agent's behavior should be driven by an AI system, not hard-coded logic.
All right. Well, I appreciate the overview, Nishant, and I hope our viewers today are writing that down. But you have another chance here because I really want to drill further down into each one of these principles. So if you could, Nishant, elaborate a little more on what you mean when speaking about principle number one.
Sure. And principle number one, if you're introducing a new agent to this multi-agent system, or if one specific agent isn't behaving properly, you can always think about and focusing the distinction of an agent based on its expertise. So if an agent isn't performing well, divide it up into sub-agents that are experts that work together on that problem that the original agent was supposed to be good at. Or if you're introducing new agents, think about it as in perspective of introducing new experts to a system that can now do more and more. And this is really why we say multi-agent systems are more accurate or faster or cheaper. It's because of the concept that the agents are experts at things and have to deal with less noise in their observations. You don't need to provide the expert the full context all the time. You can give that agent partial information of the world, which speeds it up a little, but also improves its accuracy because it has less noise to deal with. This is really the important first principle one, is just make sure you think about it in that context. Agents are experts, so just make them good at only what they're supposed to be good at, and they'll work better in the system together if you follow that principle.
Right. So in other words, make sure that you're training your agents to be hyper specialized, the very best at that one thing they do. I think that's a good one. Let's move on to principle number two. So maybe you can drill down on this for us.
Principle two is all about end-to-end performance over unit testing or individual performance of an agent. In the world of LLMs, evaluating a prompt is a very important skill or functionality in the engineering teams. But beyond just evaluating a single agent or a single prompt, it's really important to look at the overall system. The overall system, it has some emergent properties that the individual prompts don't. For example, the ability to recover from mistakes. An agent can call the wrong agent and they can go in the wrong direction and then correct themselves and come back on track, and the actual session will still be successful. The ability for a session to repair its or recorrect itself and come back and solve a problem, that's something you only get to test and see in the end-to-end performance tests. So in order to prioritize an end-to-end performance test, you might be thinking, well, now I need a end-to-end benchmark. Like, how do I design these tests? They're no longer just given an input, expect an output, and you're done. Now it's more about give a toy world example, give me a scenario, give me a situation where I can put the agent in and watch it make a couple decisions sequentially, and at the end of the session I can evaluate how it did. So you're now these tests end up being very involved to write because you have to set up these environments. These are websites we built that either the website has something wrong with it or the playwright code that's testing the website has a bug or an issue in it, and we're asking the agent to repair that test. And so since everything's been specially designed to test the overall system, we have this luxury of enforcing that the state space and action space of the agent match that of the QA engineer so that they can really interact with each other, so that when the agent is unable to solve a problem, we understand why, because we can also ask the QA engineer, hey, what would you do if you were confronted with the same problem? And then we get to close that gap and really get the AI system to be as close to human level as possible. But there's really that collaboration between the QA engineer and the AI system together that really makes this work.
Yeah, so you're really training the agent to think like a QA engineer. It sounds like there's a lot of hands-on collaboration with the QA engineers. So, I mean, what has the feedback been from the engineers working with the AI system?
Uh, some of the feedback is all about just saving time and specifically saving the monotonous, boring work that sometimes you have to do. If a flake happens, that means a test has failed. And if you were to rerun that test again and it passes, you get to move on. That isn't really enriching work. That is just you're kind of babysitting tests that aren't that reliable. That's not fun, but it is important, and that's where automation comes in. You can have the AI system do the easy stuff, just do all the stuff that feels boring or just feels like it doesn't really enrich you as a just engineer, you know. And now you get the time and the freedom to really think about those harder problems. We let the humans tackle the hard stuff and let the AI system get through that long tail of easy problems to solve.
All right. Well, thanks for elaborating. Always good to hear exactly what is the human experience working with the AI, especially again here at QA Wolf, we're really big on that human in the loop collaboration. So what do the humans think about the system? So thanks for sharing that. I think that's going to take us right into the third principle here. Nishant, could you elaborate on how you came to principle number three?
All right, principle three is avoid hard-coded logic. If you were writing JavaScript code and there was a bug in your code, you wouldn't go to the Node.js runtime and try to look at the source code and fix your bug. Your bug is likely in the JavaScript level. So the similar idea stands in a multi-agent framework. If your AI system is not behaving well, the agents are what you're programming. You're changing the behavior of the agents. So most likely the problem is with the agents. Avoid the temptation to go into the runtime, which is the AI multi-agent framework, and try to make changes in the JavaScript or Python or whatever programming language you're using. Avoid writing code in that programming language to fix your problems. Try to assume that the framework is working as intended, trust it, and instead go into the agents to make those modifications. By adding hard coded logic everywhere to fix your problem, it's a nice shortcut, but it adds rigidity to the overall system. It makes things rigid, which is a problem because we're really leveraging some of the benefits of model updates. If a large language model has been updated, then even without us touching the code or touching the overall deployment of a system in production, we can see the system improve over time. It's the opposite of software entropy. Instead of being worried that because I haven't maintained this code base for months or even years and being worried that the software will rot, we get the exact opposite experience. The system just gets better and better over time by not touching it. So we have to play with that, use that as our advantage. And you can really do that if you're not introducing more and more hard-coded logic, because that, if it's buggy, will be buggy forever. Or if it's suboptimal, will be suboptimal forever. It won't adapt to the changing environment, and you'll have to continuously maintain it.
Yeah, I think that's a really good note. Sometimes it might be tempting to take that shortcut to just get directly to the result for the short term, but ultimately you're breaking, when you're doing that hard coded logic, you're breaking the feedback loop that's going to enable the agent to get better and faster at that specific task in the long run, right?
That's right, exactly.
Well, Nishant, thanks again for providing these three core principles. I want to take it back to a more real world application. I'm sorry, I'm on a vacation state of mind today, so I'm thinking beach, man. So I want to go back to the vacation example that you provided earlier. Can you tell me a little bit more about what a multi-agent model looks like when planning a vacation?
Yeah, of course. When planning a vacation, you probably already know that it's a lot of work. You have to figure out reservations for hotels and flight bookings and all that stuff. So when you make a conversational uh, chatbot or AI system that's trying to do the same tasks that a human would, you can try to bucket it into different categories. You can try to categorize all the different things that the agent does. And as you form those categories, that is practically what the multi-agent systems are. Each individual agent is a category or a grouping in that broader conversation. So, just for example, a chit chat bot could be an agent, followed by a trip logistics agent that's really good at looking on flight information. Or you can have a calendar agent that's really good at looking at your calendar and figuring out when you're free so you can book that vacation or whatever. But when you're thinking about the vacation example, each of those separate components is practically an agent, and an agent calls a tool. A tool is a read-only action like getting the calendar info or getting the weather data or getting flight information. So agents call tools. That's kind of just an example with our running example of just the chat bot that helps you plan a vacation.
Right. So in other words, you're really, training this agent or personal assistant, you could also call it, to do all the really tedious work, trying to find the right flights that'll get you to the right hotel at the right time. But there is still that human in the loop user collaboration with the tool. You have to tell it what to do. You have to kind of give it some parameters to work on to get the job done.
Yep, that's right.
So let's take this a little more now, that back to the QA application for multi-agent models. So again, I think this is a great example you provided with the vacation. Can you tell me a little bit more about what this application looks like for software engineers?
Right. For software engineers at QA Wolf, we package this multi-agent system as a API where you can provide it a state and it'll give you an action. And now that kind of reminds you of the policy function, right? It's the same concept, just that the policy is implemented as a computational graph. When I say graph, I mean things with nodes and edges. The nodes you see here are categorized into four types. There's agents, actions, tools, modifiers. There's actually one more type called a control flow node we've introduced. But the overall picture is that just by giving it a state, we are asking the server, asking the AI system, tell me the next action to do. Then the client will perform that action to change the environment, to update the state, and then it'll call the API again. The API is called over and over and over again until the full problem is solved.
Right. And again, you mentioned the nodes there, and I just want to elaborate on that here. You've got it broken down very nicely in the graph on the screen there. Maybe you can elaborate on each one of these and what they do.
Yeah, so the agent and the tool nodes I've talked about earlier. The agent nodes are in blue here. They represent the experts. Agents can call other nodes. For example, they can call other agents to hand off the task, pass the baton to the next agent if they believe someone else can solve it. Or they can call a tool node. A tool is like an API call, a read-only action that just once you call that node, control is handed back to the agent that called it. Then in yellow over there, you see actions. Actions are things that actually change the environment. So they actually are what we return in this API call so that the client can perform that action. And then the modifier node on the left-hand side, those are nodes that change the perspective at which to look at the state. So, for example, this is kind of how we introduce hierarchical state representation. We provide an outline of, let's say, the HTML to an agent, and an agent can decide to zoom in or zoom out of the state to look at things in finer detail. There's also a control flow category of nodes that are not shown here, but probably important to talk about just for completeness. A control flow is just a way to pick the next agent without directly knowing that agent's name. For example, if we have 100 agents, keeping track of all 100 agents is a bit difficult. It just makes it a little more challenging to scale. So a control flow lets you use a shortcut reference for another agent. For example, the return control flow action is a way to pop back and call the agent that had just called you to as a shortcut. So anyways, these different nodes are practically all that there are. And then as we build the multi-agent system, we add more and more nodes to the graph. And that's kind of how we just program the AI system.
Well, thank you again for the very thorough breakdown and for providing this really detailed graph, just showcasing exactly how are these agents and nodes all working together to really get us the ultimate result that we're looking for. And of course, here at QA Wolf, the ultimate result is that 80+% end-to-end test coverage for our customers. So again, Nishant, when you think about the ultimate goal of a multi-agent model in QA, what does that look like?
A successful one would be one that saves time. It saves the engineer's time and also saves the user the time. That's kind of what we focus on here at QA Wolf 2. We're trying to build things that are not just efficient or impactful, but also things that make the engineering process faster. Since we're very engineering driven, our users are also engineers. It really goes down into the developer productivity for both the people in the engineering team implementing the AI system, and in our case, our end users who are also engineers trying to maintain the end-to-end tests. It's all just productivity for developers, giving time back for both of those users.
All right. Well, hey, I appreciate this detailed breakdown here, Nishant. Unfortunately, I do think we are about out of time. But hey, for everyone who tuned in today, watching our perspective on multi-agent AI, I just wanted to give you a little sneak peek at how the multi-agent AI that Nishant's been working at is being put to use. So QA Wolf's multi-agent AI was built under the principle that humans needed to be in the loop to deliver trustworthy and efficient results. Being trustworthy is essential to a really quality QA test, and that's what we're all about here at QA Wolf. And with expertise in end-to-end user flows, accessibility, Salesforce, Visual Diff, performance, and our recently launched Android mobile app testing, we are here with all of your testing needs. And you can learn more about this by heading to QAWolf.com and requesting a demo. Nishant, hey, I appreciate your time today. Thanks so much for joining us to share your knowledge and expertise.
Of course. Thank you so much for having me.
And for everyone joining us today, this has been Caleb and Nishant from the Wolf Den. If you want more conversations like this, you can find them by looking up Wolfed, our podcast, wherever your podcasts are found, or you can head over to QAWolf.com for more. Thanks so much for joining us, and have a great day.